Hydrogen spectrum. Hydrogen spectrum is the simplest of all atomic spectra. Hydrogen spectrum is an example for emission spectrum. Hydrogen spectrum. When hydrogen gas is filled in the discharge tube and subjected to very low pressure and high voltage, hydrogen molecules dissociate to form energetic or excited hydrogen atoms. These excited hydrogen atoms are responsible for emitting radiations. If thus emitted radiations are passed through a spectroscope, then dispersion takes place. If these dispersed radiations are allowed to fall on a photographic plate, a line spectrum is produced. Thus obtained spectrum is obtained from hydrogen, hence it is called hydrogen spectrum. In 1885, Balmer discovered a series of lines in the visible region, and this series is called Balmer series. He suggested that for any line of this series, the wave number is expressed by the equation nu bar is equal to 1 by lambda is equal to 10 96 77 into 1 by 2 square minus 1 by n square. This formula is called Balmer formula. It's applicable only to Balmer series. That is, for each line of the Balmer series, the wave number can be expressed by this formula, where n is a variable like 3, 4, 5, 6, etc. That is 3 or greater than 3. N is equal to 3, 4, 5, 6, etc. A Swedish spectroscopist, Johannes Rydberg, suggested a more general formula for expressing wave number of any line of any series of the hydrogen spectrum, and it is expressed as nu bar is equal to 1 by lambda is equal to RH into Z square into 1 by N1 square minus 1 by N2 square. This formula is called Redberg relationship or Redberg formula, where nu bar is the wave number, lambda is the wavelength, RH is the Rydberg constant. And its value is 10 96 77 centimeter inverse. N1 is a constant and N2 is a variable. Throughout a series, that is, N1 will be a constant for a particular series and N2 will be a variable. Different energy levels of the hydrogen atom can be drawn as follows. N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4, N is equal to 5, N is equal to 6, 7, 8, say n is equal to infinity. This is E1, E2, E3, E4, E5, E6, E7 and so on. See, when an electron get de-excited from second level to the first level, then some radiations are emitted and a line is produced. If third to first occurs, a line is obtained and so on. That is de-excitation, all de-excitations takes place to n is equal to 1 level. And the corresponding spectrum is called, or the series is called Lyman series. It falls in UV region. If the de-excitation takes place from third to second level, fourth to second level, fifth to second level and so on, then a series of lines is produced and that series is called Balmer series. That series is obtained in the visible region. See, if N1 is equal to 1, N2 is equal to 2, 3, 4, 5, etc. That series is called Lyman series and it falls in UV region, UV ultraviolet region. Then if N1 is equal to 2 and N2 is equal to 3, 4, 5, 6, etc. N2 is equal to 3, 4, 5, etc. That series is called Balmer series. Balmer series. It falls in visible region. If de-excitation takes place from fourth to third level, fifth to third level, sixth to third level and so on, then a series of lines is produced and it is called Paschen series. It falls in IR region. If N1 is equal to 3, N2 is equal to 4, 5, 6, 7, etc. That series is called Paschen series. It falls in IR region. Now, if de-excitation takes place from 5th to 4th, 6th to 4th and so on, see like this, then a series of lines is produced. It is called bracket series. It falls in IR region. If N1 is equal to 4, N2 is equal to 5, 6, 7, 8, etc. That series is called bracket series. Bracket series. It falls in IR region. If N1 is equal to 5, that is, de-excitation takes place from 6 to 5, 7 to 5 and so on, a series of lines is produced and it is called fund series. See, N1 is equal to 5, N2 is equal to 6, 7, 8, etc. That series is called fund series, P-F-U-N-D, fund series. And it also falls in IR region. See, these are the 5 important series of lines in hydrogen spectrum. Yet another is also important. That is, if de-excitation takes place from 7 to 6, 8 to 6 and so on, then a series of lines is produced called Humphrey series. See, if N1 is equal to 6, N2 is equal to 7, 8, 9, etc., that series is called Humphrey Series. It also falls in far infrared region, far IR region. See, these are the important series of lines in hydrogen spectrum. See, in this expression, that is Redberg formula, Z stands for the atomic number. For hydrogen, Z is equal to 1. And for He single plus, Z is equal to 2. For Li2 plus, Z is equal to 3. See, Rydberg relationship is applicable only to single electron systems, that is spectra of single electron systems like H. H is single plus. H is single plus contain only one electron. Helium contain 2. Removal of one electron forming a positive charge. So we get H is single plus. There is only one electron. Li2 plus also contain only one electron. So the spectra of these species obey Redberg rule or Redberg formula. And for these, hydrogen Z is equal to 1, He plus Z is equal to 2, Li2 plus Z is equal to 3. It's very important. And these series of lines are to be remembered in a sequence because the values of N1 and N2 changes continuously in a sequence. And these series can be remembered by a simple short form. See, Ly, Ba, Pa, Bph. Here, Ly stands for Lyman series. Ba stands for Balmer series. Pa stands for Parsons series. B stands for bracket series. P stands for fund and H stands for Humphrey series. So, see, let this be the name of a person, Libapa. BPH are the initials. Then we can say that Ly stands for Lyman, Ba stands for Balmer, Pa stands for Parsons, B stands for bracket, P stands for fund, and H stands for Humphrey. See, for Parsons series, 1, 2, 3. So N1 is equal to 3 and N2 is equal to 4, 5, 6, 8, 7, 8, etc. See, for bracket series, 1, 2, 3, 4. So N1 is equal to 4, N2 is equal to 5, 6, 7, 8, etc. So it is very easy to remember the sequence and the values of N1 and N2 from this short form. We have Redberg relationship. Nu bar is equal to 1 by lambda is equal to RH into Z square into 1 by N1 square minus 1 by N2 square. Here Z stands for the atomic number. If Z is equal to 1, it's for hydrogen. If Z is equal to 2, it's for He single plus. If Z is equal to 3, it's for Li2 plus. See, such species are single electron systems. See, hydrogen has 1 electron, He plus has 1 electron, Li2 plus has 1 electron. So, Redberg relationship is applicable to spectra of single electron systems like H, He plus, Li2 plus, etc. See, in this relationship, 1 by RH value is very important for calculating the wavelength of a particular line in a series. See, 1 by RH value can be expressed as 1 by RH is equal to 1 by 109677 centimeter inverse. That is equal to 9.118 into 10 raised to minus 6 centimeter. Centimeter inverse become centimeter. See, this can be expressed in meter. By dividing by 10 square, that is 100. That is 1 by RH is equal to 9.118 into 10 raised to minus 6 divided by 10 square. That's equal to 9.118 into, see, 10 raised to 2 become 10 raised to minus 2, so 10 raised to minus 8. It can be expressed as 1 by RH is equal to, see, displacing 2 decimals to the right, that is 911.8 into 10 raised to minus 10 meter. 10 raised to minus 10 meter is equal to 1 angstrom units, that is equal to 911.8 angstrom units. See, this value is very important for doing simple numerical problems in connection with the calculation of wavelength of each line in this series. Now let us check the wavelength of various lines in a given series of hydrogen spectrum. Let us check Lyman series. See, for Lyman series, for the first line, N1 is equal to 1 and N2 is equal to 2. See, for the first line, N1 is equal to 1 and N2 is equal to 2. Therefore, substituting in Redberg formula, 1 by lambda is equal to RH into Z is 1 by N1 square, N1 is 1 minus 1 by N2 square, N2 is equal to 2. That is equal to RH into 1 by 1 square minus 1 by 2 square. Therefore, 1 by lambda is equal to RH into, see, this is 4. This is 4 minus 1. That is RH into 3 by 4. Therefore, lambda is equal to, see, reciprocal of this. That is 4 by 3 into 1 by RH. That is 4 by 3 is 1.33 into 1 by RH is, see this value, 911.8 angstrom units. This is the wavelength for the first line in Lyman series. Now let us check for the second line. For the second line, see, for the second line, N1 is equal to 1 and N2 is equal to 3. N1 is equal to 1 and N2 is equal to 3. So for the second line, 1 by lambda is equal to RH into 1 by 1 square minus 1 by 3 square. That is equal to RH into, see, this is 9 minus 1. That is RH into 8 by 9. Therefore, lambda is equal to reciprocal of this. That is equal to 9 by 8 into 1 by RH. See, 9 by 8 is equal to, that is 9 by 8 is equal to 1.125. 1 by RH is equal to 911.8 angstrom units. See, this is the wavelength for the second line of the Lyman series. Second line of the Lyman series. Now let us check the wavelength of the last line of Lyman series. See, this is the last line. N is equal to infinity. N1 is equal to 1, N2 is equal to infinity. N1 is equal to 1 and N2 is equal to infinity. 1 by lambda is equal to RH into 1 by 1 square minus 1 by infinity square. That is RH into see any number divided by infinity or infinity square is equal to 0. So this is 1. Therefore RH into 1. Therefore lambda is equal to reciprocal of this. That is 1 into 1 by RH. That is equal to 1 by RH is 911.8. Therefore 1 into 911.8 angstrom units. See, this is the wavelength for the last line of the Lyman series. See, from these calculations it is clear that the wavelength value will be maximum for the first line, that is 1.33 into 911.8. For the second line it is slightly decreased. See, for the second line it become 1.125 into 911.8. But for the last line it become 1 into 911.8 angstrom units. For the last line lambda value is minimum. For every series the first line has maximum wavelength and last line has minimum wavelength. So the wavelength of the last line in a given series is called series limit. Series limit. See, for Lyman series, the series limit value is 1 into 911.8 angstrom units. Similarly, every series has a series limit. That will be the wavelength of the last line of that particular series. For such a series, the first line has maximum wavelength in the given series. That's all. Question. What transition in hydrogen spectrum could have same wavelength in Balmer series of HE plus spectrum for the transition from n is equal to 4 to n is equal to 2. Say, we are asked to find the transition in hydrogen spectrum with the wavelength that corresponds to the transition from n is equal to 4 to n is equal to 2 in HE plus spectrum. That is, we are asked to find the wavelength of the hydrogen spectrum that corresponds to n is equal to 4 to n is equal to 2 transition in HE plus spectrum. See, first of all, we are going to find the transition, that is wavelength of the transition in HE plus spectrum. For HE plus, Rydberg relationship is 1 by lambda is equal to RH into Z square into 1 by N1 square minus 1 by N2 square. Here Z is 2 for HE plus. Therefore, RH into 2 square into 1 by the transition in HE plus is from n is equal to 4 to n is equal to 2. So 2 square minus 1 by 4 square. That is 1 by lambda is equal to, so this is 4. So RH into 4 into, so this is 16 and this is 4 minus 1. Therefore, RH into 4 into 3 by 16. See, we get 4 here. Therefore, 1 by lambda is equal to RH into 3 by 4. Taking reciprocal, lambda is equal to, see, reciprocal of this, that is 4 by 3 into 1 by RH. Now let us check for hydrogen. See, 1 by lambda, Redberg relationship is 1 by lambda is equal to RH into Z is 1. So 1 by N1 square minus 1 by N2 square. Here the values of N1 and N2 are not known. They are to be determined. See, their values can be determined by guessing. That is by trial and error method. Let us check. Suppose N1 is equal to 1 and N2 is equal to 2. Substituting here, say 1 by lambda is equal to RH into, say 1 by 1 square minus 1 by 2 square, that is equal to RH into, see, this is 4 minus 1, that is equal to RH into 3 by 4. Therefore, lambda is equal to reciprocal of this, that is 4 by 3 into 1 by RH. See, for He plus, the wavelength of the transition from n is equal to 4 to n is equal to 2 is 4 by 3 into 1 by R. This is equation 1. 1 by RH. This is equation 1. And for hydrogen, now lambda become 4 by 3 into 1 by RH. That is equation 2. See, the left hand side of equation 1 and 2 are the same, and right hand sides are also the same. Therefore, it is clear that both the transitions are having the same wavelength. Now, coming to the question. See, n is equal to 1 and n is equal to 2 is for the first line in Lyman series. First line in Lyman series. So, the wavelength of the transition from n is equal to 4 to n is equal to 2 in He plus spectrum will be the same as the wavelength of the first line in Lyman series of hydrogen spectrum. That's all. Question. Find number of lines in spectra for the following transitions. First question, N1 is equal to, n is equal to 7 to n is equal to 2. Second, n is equal to 5 to n is equal to 2. Third, n is equal to 3 to n is equal to 1. In order to calculate the number of lines, we can use the formula here, n2 minus n1 into n2 minus n1 plus 1 the whole divided by 2, where n2 is a higher value and n1 is a lower value. Let us check for the first transition, that is n is equal to 7 to n is equal to 2. See, for this transition, N2 is 7 minus N1 is 2. So 7 minus 2 into 7 minus 2 plus 1 the whole divided by 2. This is 5 into 5 plus 1 6. 6 by 2 that is equal to 30 by 2 is equal to 15. See, 15 lines are formed when the transition takes place from n is equal to 7 to n is equal to 2. Now, let us check for the second transition, that is n is equal to 5 to n is equal to 2. Here, 5 is the highest and 2 is the lowest value, that is 5 minus 2 into 5 minus 2 plus 1 the whole divided by 2. This is 3 into, see, this is 3 plus 1, 4 divided by 2 is equal to 12 by 2 is equal to 6. So, 6 lines are formed during the transition from n is equal to 5 to n is equal to 2. Now let us check for the third transition, that is the higher value is 3. So 3 minus 1 into 3 minus 1 plus 1 the whole divided by 2 is equal to, this is 2 into 2 plus 1 3, 3 divided by 2, that is equal to 3. See, 3 lines are produced during the transition from n is equal to 3 to n is equal to 1. Let us check whether they are correct or not. See, this is n is equal to 1, 2, 3, 4, 5, 6, 7. Consider this transition 7 to 2. See, so 5 lines are produced. See, 4 lines are produced. See, 3 lines are produced. 2 lines are produced and 1 line is produced. See, 5 plus 4, 9 plus 3, 12 plus 2, 14 plus 1, 15. Therefore, 15 lines are produced during the transition from 7 to 2. Now, let us check for this, that is 5 to 2. See, n is equal to 1, 2, 3, 4, 5. See, first line, second line, third line. See, there are 3 lines, there are 2 lines, and there is 1 line. Therefore, there are 3 plus 2 plus 1 is equal to 6 lines during the transition from n is equal to 5 to n is equal to 2. See, let us check for this transition, that is n is equal to 3 to n is equal to 1. See, this is n is equal to 1, 2, 3. There are 2 lines here. There is 1 line here. So, there are 3 lines for the transition from n is equal to 3 to n is equal to 1. That's all. Question. Consider an electron of H atom undergo transition from n is equal to 2 to n is equal to 1. Calculate the wavelengths and frequency of transition. See, we are asked to calculate the wavelength and frequency corresponding to transition from n is equal to 2 to n is equal to 1. We can apply Redberg formula here. That is, nu bar is equal to 1 by lambda is equal to RH into Z square into 1 by N1 square minus 1 by N2 square. Substituting with values, 1 by lambda is equal to 109677 into Z is 1 for hydrogen. See, N1 is equal to 1. So 1 by 1 square minus. N2 is equal to 2. So 1 by 2 square. That is 109677 into, see, this is 4. This is 4 minus 1. That is equal to 109677 into 3 by 4. See, lambda is equal to reciprocal of this. That is 4 by 3 into 1 by 109677. That is equal to 1.216 into 10 raised to minus 5. The value, this is 1.216 into 10 raised to minus 5 centimeter. See, 100 centimeter is equal to 1 meter. Therefore, centimeter can be converted into meter by dividing by 100. That is 1.216 into 10 raised to minus 5 divided by 10 square. That is equal to 1.216 into 10 raised to minus 7 meter. That is, lambda is equal to, see, 121.6 into 10 raised to minus 9 meter. 121.6 into 10 raised to minus 9 meter. This is the wavelength value. See, 10 raised to minus 9 meter is equal to 1 nanometer. So we can convert this into 121.6 nanometer. Now we are asked to calculate the frequency also. We know that nu is equal to C by lambda. C is 3 into 10 raised to 8 meter per second. And lambda is, take the value in meter, that is 121.6 into 10 raised to minus 9 meter. Meter getting cancelled off. We get 3 by 1.216 into, see, this is 10 raised to minus 7. Why? Because 10 raised to 2 is taken from here. 10 raised to 2 into 10 raised to minus 9 is equal to 10 raised to minus 7. So 10 raised to minus 7 into 10 raised to 8 per second. This become, see, 3 by 1.216 is equal to 2.467 into, see, 10 raised to minus 7 comes in the numerator as 10 raised to plus 7. So 10 raised to 8 into 10 raised to plus 7 is equal to 10 raised to 15 per second. So frequency of the corresponding transition is 2.467 into 10 raised to 15 per second. That's all.